Good afternoon. Thanks for coming. My name is Jeroen. I'm from Belgium, and I'm here today to talk a bit more about how you can use some of our open source tools to integrate InfluxDB into an industrial environment. So a bit about our company, Factry. So we're a company founded about 3 years ago in Ghent, Belgium, and we focus on making industrial software solutions. So basically we want to provide people in factories and operational environments with tools to optimize how they work, to be more efficient. So data-driven tools for operational improvement. One of those tools is Factory Historian, which I will come back later. It's a product that's heavily based on using InfluxDB as a data store in the back end. And yeah, we use a lot of open source. So basically we use a lot of open source in our solutions, but we also, when possible, contribute back. If we develop some tools that are not our core business, we try to give it back to the community, as we get a lot from it as well. And also, a bit of a commercial, we are having a time series meetup in Belgium as well, in Ghent. So we host it about 2 times a year at our office in Ghent. So if you're ever around in Ghent, please check out, the slides will be available afterwards. If you're ever around, please feel free to join us and perhaps also submit a talk, because we're always looking for speakers and would be very nice. But today I'm going to talk about industry. So a bit of a different context than most of the talks we've been hearing over the past 2 days. We're going to talk about industrial IoT, or the Internet of Big Things. But in Europe, we typically call it Industry 4.0. I don't know if you're familiar with the term Industry 4.0. It's a term, it's a name coined by the German government, and it's basically 4.0 means it's the 4th industrial revolution. So everything around digital manufacturing. So short pop quiz, does anyone still remember from high school what the first industrial revolution was? It's like steam, indeed. So some 300 years ago, people invented steam power, and that meant a really big revolution. Mechanization, factories were popping up like nothing, especially here in the UK. So it had a really big impact on life and economy in general. Ah, damn, too fast. What was the second industrial revolution? So about 100 years ago, we all know Henry Ford and Ford Model T. So mass assembly was introduced, and it was the first time people started thinking about how can we create more products with the same amount of resources, with the same amount of people, how can we be more efficient? Second industrial revolution. And then along came computers. So in the 60s, 70s, 80s, computers started coming into our daily lives, and also in process automation. So people heavily started automating processes. They added sensors to the process, actuators, controllers, and most of the process steering was from then on done with digital tools, actually. So basically, when you have a process, like a fermenter or a brewing kettle, you start instrumenting it, you add sensors, temperature sensors, pressure sensors, and so on. These sensors send their input to a PLC, a programmable logic controller, which then does something with it and gives a signal back to an actuator to control the process. So for example, temperature is too high, I will slow down any heating, or I will start cooling, that kind of stuff. So all of this is managed by controllers, and if you have a lot of these processes, typically also there is a supervisory control system, which we call a SCADA system, and SCADA systems control many sub-processes, are connected to many PLCs, and thus control a whole process. And a lot of human interfaces are also connected to that. So the 4th industrial revolution, which is happening today, is all about digitalization, cyber-physical systems, artificial intelligence, machine learning, to cope with all the complexity that a typical factory has to have today. I don't know, has any one of you been in a factory recently? Did it look like this? Mostly it doesn't. So experience shows us that there is actually, to this day, a big gap between what we call OT and IT. OT is for operational technology. So even though computers and automation had a lot of effect on processes, you can see that these are actually two different worlds, and they have grown their own technology, and up till today they use different kinds of technology. So there is a gap in between them, and there are probably a lot of reasons for that, but I can think of 3 at this time. We have very long life cycles. So if you put in a production line, if you put in a factory, you don't get it out in 2 years and put all kinds of new stuff in there. You have a factory running for 10 years, 20 years, 30 years. So that means that the systems controlling these factories are also having very long life cycles. So sometimes we have to go full retro. We recently had to interface with SQL Server 2000, which was kind of old. So we had virtual machines with Windows 2000. Does anyone remember the boot sound of Windows 2000? It's pure nostalgic. The second one is slow adoption. Automation people tend to be very conservative, and it's kind of makes sense. They build machines, they build processes, people work with those machines, so they want to use technology that works. But there is this kind of dogma that it has to be at least 5 or 10 years old before they are sure that it works. So that means that when you build a factory today, most of the technology you put in is at least 5 years old. So it has also an impact. 5 years, that's a huge amount of time in the IT world. So yeah, it also has an impact, and why there is this gap in technology. And then lastly, vendor lock-in. So we have a lot of big industrial companies who sell controllers, sell control systems, and each of those companies develop their own standards, and they are the only one to implement that standard. So it's very difficult to communicate between different vendors, different devices, that kind of stuff. So everyone kind of has their own standard, which makes it difficult from the situation we were. So everything is well instrumented, data is available somewhere, but it's hard to get it up to external applications. I remember the slide from Evan yesterday, where we were the 4 steps: instrument, observe, learn, and then automate. I have the feeling we're stuck between the observe and learn phase. So we have the data, we have people looking at it locally, but nobody has an overview. It doesn't connect to external systems, and certainly not to algorithms or machine learning or that kind of stuff. So basically, there's still a gap there. And then now we've established that context, let's have a look at what kind of time series data we actually have in industry. So when we compare it to a typical DevOps use case, so we've heard a lot of DevOps talks over the past 2 days, we have different kinds of data. And also, so the typical metrics, where in DevOps you have CPU loads, disk IOs, database statistics, application requests per minute. In industry, we have sensor data. Temperatures, pressures, valve states, flows, I don't know, control signals. We record basically everything we can record. In regards to resolutions, DevOps typical seconds to minutes. In industry, especially for critical control parameters, we can go really sub-second to the millisecond level. And then whereas typically we also do downsampling after a few weeks, in DevOps we really keep our data at the highest resolution for many years. So this is also related to the main goal of the data collection within industry, whereas we have more real-time monitoring and performance monitoring, incident alerting in DevOps. For industry, there is also a big driver from the quality guarantee. If I create, for example, a food product and I get a customer complaint or a food safety issue, I need to be able to look back at the exact time that product was produced. What was the temperature of my sterilizer, for example? Did it drop below a certain critical threshold? So it's more historical analysis than real-time monitoring, our use case within industry. We also have monitoring, but just generalizing a bit. So we've been recording data for decades. Not me, but people in industry. So I present to you the first time series database. This is actually the way people recorded critical process parameters decades ago. So I was talking about a sterilizer. You need to be sure if you produce food that you actually adhere to the highest quality standards. So this is what people did back then. So they still do it. They still do it, yeah. As I said, yeah. These systems tend to be in place for multiple decades. So yeah, at my last employer, these systems were also still in place on the oldest sterilizers. So mechanical time series databases, very simple query language though. But over the years that followed, people started their group, different markets. People started developing process historians. So basically, they developed software to allow data collection from industrial systems and to visualize them. And this is the result of those systems. So I don't know if you heard about OSIsoft Pi. They're kind of a big company in that space. They released their first historian solution in 1985 or something. So back then, we already had kind of time series databases. So when you start looking, what does a process historian do? It's a database software application that logs or historizes time-based process data. So when I read that a few years ago, it sounded very similar to what Influx is doing these days with time series data, but they do it with modern technology. So why not use InfluxDB to historize process data? And by using InfluxDB, a more open database, IT technology, REST APIs, no industrial protocols, we can open up all this data to these external applications and have people, data scientists, I don't know, do whatever they want with it. So we actually open up the industrial data to the IT space. That was the main goal, to do so. So all we need now is a communication protocol to get the data out the process layer. And that's why we developed some things around OPC-UA. So I told you earlier, there were no standards in industry. There is actually one, but it's quite a recent one. So it became adopted over the last 10 years. This OPC-UA. So it's kind of a vendor-independent communication protocol for industry. And it's actually the successor of OPC, which stands for OLE for process control, which was a very old version relying on Microsoft's DCOM, which was very messy to work with. But this one is actually TCP-based, it's open, it's vendor-independent, platform-independent, so it can actually, is a fit for purpose for what we wanted to do. And every vendor is already integrating it on their latest controller. So it's not that they only speak their own language anymore, they started integrating OPC as a communication protocol on their latest controllers. And we can also retrofit it on older ones, older machines, software-based or hardware-based. It depends a bit. So this is what typically, when you connect to an OPC-UA server, you get this big hierarchical tree where you can browse your controller, access all the memory spaces, get data from it. So it's a different structure than InfluxDB. That's the first remark. So where we have this tag-based, metadata-based data model in Influx, here we have really a hierarchical, browsable data model. So we will need to map that later on. And it's important to know that every node in the system is identifiable by a single unique node ID, what we call it. So we'll use that later to collect data from the server. So we'll use OPC-UA to get the data into Influx. And that was the first thing we did as a company a few years ago, is to write a data collector, an OPC-UA data collector for Influx. And this version is still open source. It's available on GitHub, and you can just configure it to read data from OPC-UA sources. It buffers the data locally because in case of network interruptions, you don't want to lose any data. So it buffers the data, and when the connection comes back online, pushes it to Influx, and you can just download it there. And I was going to show you quickly how that works. So I don't have an actual device, but I will use an Opc-Ua Simulation Server. Should be booting right now. All right. So just to show you how this stuff connects to one another. So now I started an Opc-Ua server. I will connect to it using a client just to show you how these things work. I don't want security right now. There we go. So we get our address space. So as I mentioned, a hierarchical structure with folders and devices. For example, I have objects, and then I have a device, and under that device I have different parameters. So for example, the level of this device is something I can read from this OPC-UA server. So I'll monitor this one, put it a bit larger. So you can see here the node ID, and you can see that the value is actually going down a bit, and I can even graph it like this. There we go, eat that, Grafana. So that's how OPC works, so quite simple. So how do we get this data into Influx? So we go to GitHub, we download our OPC-UA logger project, and then you need to identify all the nodes you want to collect data from. So you'll need these. The node IDs. So these actually identify a single data point, a sensor value, a memory registry in a controller, that kind of stuff. So you download the logger, and then you can go create a config file. You put in the endpoint of your OPC-UA server. In this case, there's no security, so I don't need to worry about that. That's your input. Then your output, your Influx database. So mine is running on localhost. I have 2 Dockers running. There we go. So I have an InfluxDB and a Grafana running. So I'm running this one on localhost. I have a username, password, a database, that kind of stuff. And then lastly, you need to configure which data you need collected. So you have a few measurements. In this case, I have a sinusoid measurement, so it's simulated data. I have the level I showed you earlier, and a bit lower, I also have a random number. There we go. And you can see there are 2 ways of collecting your data. You can either pull it, that's scraping, every 1 second, every 5 seconds, I need this value, or you can have a monitored value, which basically tells the OPC server, send me this value when it's changed. We use this specifically for valves, for example. You don't want open, 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 open every second or every half a second, but when it does change state, you want to know exactly when the state was changed. So that's typically a use case where you would use monitored. And then you can also add some tags that will be written together with the value to InfluxDB. So then, let's hope this all works. Yeah? There we go. So the logger connects to the OPC server, connects to Influx, and then just starts streaming data into Influx. So we have this simulation server here still running. Let me go to Grafana. There we go. So this is just a graph that plots all the data that's in the database. So we can see that the data starts coming in by using this logger. So you can just configure this with all the metrics you want. We've been running it with thousands of metrics in the same config file. You just configure it, play it as a service, and you can start collecting data from OPC-UA. So that's basically how that works. We're releasing a new version very soon. This is quite an old one. It's been written in Node.js 4 or 5, I think. So the new one will have cleaner code because now we have async await, which previously wasn't available. Better buffering, and we'll also implement a packaging mechanism so we can deploy it as a single binary, which is very relevant if you want to deploy it in an industrial system. You don't want to install Node.js, and that's you just want to put a binary, no external dependencies, done. So that's basically what we're doing right now. So what can you actually do with it, or what do we do with it with some of our customers? Let me present again. There we go. So this is a bioreactor somewhere in Ghent, so a fermenter, and you can easily see that this is not the same types of graph you usually see in a Devops use case. You can see the individual batches being produced at a certain frequency in time. The white one is the fill level, so when the tank is filled for the reaction, and then the red one is the temperature. So it's being kept relatively constant, and after each batch it goes up for cleaning, so for sterilization. So that's one of the use cases. Another one is energy monitoring. So most factories already have a lot of energy sensors, power sensors, that kind of stuff installed, but nobody's doing anything with the data. So when you just start, these are counters, so kilowatt counters and usage counters, they just go up and up and up all the time. But if you use some of the InfluxDB query functions, so to calculate, for example, differences on minute base, you can really get consumption patterns from them. So you can already start learning new things from data that was available somewhere, but you just, nobody was using it. And a third use case, but maybe I can show this. I think this one's a live one. Yeah, this one's pretty cool. Wind turbines. So wind turbines actually use the same industrial control systems as normal factories, SCADA systems. So we have one customer in the port of Antwerp who is running a lot of wind turbines. We dropped data collectors at each wind turbine, or each, I don't know how you call it in English, where they are all connected to the power grid. There's a control system, so we put some data collectors there, and they start pushing their data to Influx, and then you can create these dashboards. Camera is not coming from Influx, by the way. All right. So for this use case, we went one step further as well. So these people were thinking, okay, now we have all this data, we can do cool stuff with it. We have written an algorithm that does some calculations for us and is able to decide whether a wind turbine should stop operating in case of certain parameters like nuisance for neighbors or something like that. So they asked us, can we give back that signal to the control layer? Because now we get data out the control layer, but now they want to get it back inside the control layer to give a decision back to the wind turbines. And for that, we also, so basically you have your algorithm here. We want to get it back to the control layer. So what we've done is we just write the decisions back into InfluxDB. So the algorithm processes data, writes it back to a new measurement in a new database, for example. And then we expose some measurements of that database over OPC-UA. So I was collecting data from an OPC-UA server earlier. Now we expose data that's in InfluxDB back over OPC-UA so the control system can connect to it. And we've also written an open source tool to do this. So it's a bit the same concept. You have, again, a config file. I'll just start a new session here. There we go. So I have this config file. I just say, please run on this port. This is the InfluxDB you have to connect to. And these are the measurements you need to expose. So in this case, the two measurements I was collecting earlier. So I was collecting them, and now I want to give them back. That's nothing fancy, but normally it's something different. There we go. So building server space, running, and if I go back to my fantastic client here, and I disconnect from the old one, and I go to localhost 7000. There we go. You can see that my database, which was called InfluxDays, is now exposed over in my hierarchical browse tree. I can open it, and I have my measurements from the config file exposed here as as OPC-UA nodes. So one of the difficulties we had here is the fact, again, the data model. So InfluxDB has the tag-based, metadata-based data model, and we had to kind of flatten it out to match with this kind of structure. So what we've done is we've taken each measurement as a separate folder, and then each set of tags, so each series is exposed as a different node. So that was the thing we came up with. If anyone would have better suggestions, please let us know. So again, we can just have a look. No. And we can start monitoring the value that's coming from InfluxDB this time. So you should be able to see a change. Yeah, there we go. So this way you can give results from algorithms from I don't know what back to the the control layer. So finally, to wrap this all together, I just wanted to give some feedback on how Flux is important for us, because we've been working with InfluxDB for 3 years now from the 0-point version. We've had a lot of customers working with Influx as well, and asking questions to us. And one of the questions that came back, it's the same for everyone, math across measurements. So there's this company that creates water purification systems. And a typical KPI for a water purification system is the pressure at the input versus pressure at the output. The pressure drop, because it's a measure for how dirty your filter is. If pressure drop increases, that means your filter is dirty and you have to replace it. So basically they have two pressure sensors, input, output. Can we know the difference? No, you can't. But now with Flux, this is easy. Math across measurements. So we take the input pressure, the output pressure, and in the result of a Flux query, we just calculate the difference, and you can see indeed that over a few days, the pressure drop starts building up at a certain point where they have to replace the filter. So that's 2 buckets. So you create 2 series, sensor 1, sensor 2, and then you join them for creating the calculation you want. That same customer had another question, and this one was a bit more difficult. So they have a sensor, a turbidity sensor, that's measures the turbidity of the water going through. And they wanted to do some calculations, or they just wanted to see that data in function of the status of the machine. I don't care about this data if the machine is not running, because the sensor keeps sending data, but it's just nonsense data. So they have one tag with the turbidity, another measurement with, another measurement with the machine status. Can you combine the two to show me only the turbidity when the machine is running? So that would not have been possible in InfluxQL. But with Flux, we managed to do it. So this is the machine status. It's an integer status that goes from whatever, but 2 are relevant for our use case, status 11 and 21, I guess. So in the first part of the query, we interpret the status to a 0 or a 1, running or not running. Then we get the value from the turbidity sensor, and you immediately see that there's a lot of noise on the data when the machine is not running. And as a final result, we just combine these two and show me the data if the status is 1, and don't show me the data if the status is 0. This is now pure visualization, but you can then, if you want to calculate efficiencies or something like that, you only want to do that when your machine is running. All the other data doesn't matter. So this is really, it's quite more complex query. I'm not going to explain it, but you can look at it afterwards. But yeah, Flux allows us to do this stuff, which makes it very powerful, because if we wouldn't have had Flux, we would have said, we'll write you a custom daemon that processes the data and feeds it back inside into a new time series. So this makes life a lot more easy for us. So that was my talk. I don't know if you have any questions. Please feel free.
You see that there is a higher retention policy.
Mm-hmm.
Have you had any problems storing and keeping all that data in Influx?
Not yet. So we have customers where we migrated their old system, and we have more than 8 years of data now, I think. It's not at a very high cardinality, but well, at second resolution. I think it's about 2,000 metrics at second resolution, and it's yeah, no problem so far. I hope it stays that way. At this time, this was written for. Yeah. So the way we did it, we have the OPC-UA side, we have the InfluxDB side. If you drop in another database library, you could use it to write to something else. It's the same principle, but we needed it for Influx, so we wrote it for Influx.
Do you plan to include other protocols like 6150 or something like that?
We are looking at other protocols. OPC-UA is not the only data collector we have, because we have collectors for CSV files, other relational databases. We even have a data collector for Microsoft Excel. But we're looking at other protocols as well. But we typically implement new stuff as we encounter them. So we haven't encountered that one at our customer yet, so not yet.
Have you seen any limitations on high frequency data being pushed through the OPC-UA influx port?
High frequency data, we've seen some limitations on the OPC-UA side, especially when you start working with controllers and then a software-based OPC-UA server on top of that. If you go to 10 millisecond resolution, then it can become a bottleneck. But in most cases, the bottleneck was related between the device itself and OPC-UA, and not on the side where we did the data collection to Influx.
Yeah, so you fix it at the hardware level or
yeah.
before the OPC-UA?
Yeah, we have a high resolution, high frequency use case now where we are actually looking on how can we get this frequency as high as possible. So yeah, they were looking at other hardware at the moment. Yes?
Do you have different instances for each customer, or do you store everything in the cloud?
Well, we have cloud instances, but each customer has its own instance because, yeah, industry data. Some of the customers also already put it in the cloud, but most of them host it on-prem still because of. Yeah, yeah.
So these scripts run on the OPC server at the factory.
Mm-hmm. Yeah. Yes.
I'm also thinking about putting the InfluxDB
Onto
onto the PLC.
the PLC.
Yeah, because now these days, like Siemens have new open controls like back office and PC
Yeah.
with PLC on it.
Yeah.
You can also put the Influx onto the target.
In theory, you could. Yeah. So we've already had some discussions around it, but we haven't developed anything to do here.
Disk cycle or something? Or what is the problem? Why you shouldn't do it on target itself? Is it about the disk that gives problems? Or?
Nothing I can think of specifically. We just didn't encounter any use cases yet where we would need such kind of deployment. We have had discussions for on-device deployments, just theoretical, but nothing practical yet. Sorry. Yeah, but most recent PLCs, they start having like ARM-based processors inside them, and they open up. They have like this real-time processing part and also this more computing part. So you can. Yeah. Okay. So if you have any further questions, I'll be around. And thanks for attending.